Imagine you're on the London Underground, or the Tube, and you're trying to get from Piccadilly Circus to Tottenham Court Road. There are at least three routes you can take. You can take the Piccadilly line to Leicester Square, then the Northern line to Tottenham Court Road, or the Bakerloo line to Oxford Circus, then the Central line to Tottenham Court Road, or the Piccadilly line to Holborn, then the Central line to Tottenham Court Road. Which one is faster? Well, one method to figure this out would be to just count the number of stations. So if we take Route 1 and 2, we only encounter 2 stops, while Route 3 requires 4 stops. However, it could be that some of these journeys take a lot longer than others, say the tracks are a bit old or something. So how would we deal with this? Of course, we could just consider all the possibilities, then calculate the total distances and compare them, but this could be extremely costly for more complicated journeys. So, is there a better way? Of course, it's called Dijkstra's Algorithm, and it was cooked up by the Dutch computer scientist Dijkstra in the 1950s. And this algorithm basically allows us to just find the shortest path between any two nodes in a graph, where a graph is just a bunch of nodes and the edges that connect them. Now, by short, we generally mean the path that minimizes some kind of cost, of which a certain cost value is assigned to each edge. Now, the cost could be time if you're trying to get somewhere as fast as possible, or it could be ticket cost if you're trying to be as economic as possible. For example, in air travel, where sometimes the quickest flights are also the most expensive, and so on. But in the abstract, all we have is some cost attached to each edge, and we're trying to minimize this cost along the path. So, how does Dijkstra's algorithm work? Well, the basic idea is that we try to find the shortest distance from the start node to each node in the graph, regardless of the path taken to that node. And then we can use this knowledge to construct the path taken to that node that achieves this minimum cost. So now I'll go backwards and show how the second step works first. So imagine we have this graph and we're trying to find the shortest path from A to D. Imagine that we also know in advance that the shortest distance to D is 8, and the shortest distance to C is 3, and so on. And of course, the shortest distance to A will always be 0. So now we know that the last leg of the journey has to be from B to D. This is because 8 minus 3 is 5, so we know that we have to visit B before D in order to achieve the minimum distance of 8. Conversely, 8 minus 9 is not 3, so we know that we don't go from C to D. Now, what we do is repeat the same step with B in a sort of backwards propagating manner. So we know that the minimum distance to B is 5, and we know that the penultimate leg is A to B, not C to B, since 5 minus 5 is equal to 0. So now we know how to find the shortest paths given the shortest distances, but we still don't know how to find these shortest distances in the first place, and that turns out to be the main bulk of Dijkstra's algorithm. Again, I'll demonstrate with an example. So imagine we're trying to get from A to H. So first, we want to find the shortest distance to H, as well as the shortest distance to every node that could be involved in the path to H. And then after that, we'll do the backwards propagating steps that we just saw. So how do we find these distances? Well, first, we place each node into one of 3 categories: unvisited, visited, and current. So at the beginning of the algorithm, every node is unvisited. Now second, we give each node a tentative distance, or current distance value. At the beginning, every node has a current distance of infinity, while the start node has a current distance of 0. Now the objective is to update these distances as the algorithm goes on, such that they will end up representing the shortest distance to each node from A. Now with this, we can start our forward pass. So we start by setting node A as our current node. The idea here is that we then update the distance to each direct neighbor of the current node by calculating the minimum distance to that neighbor through the current node. In other words, calculating the minimum distance to the neighbor across all paths that include the current node. And the way we do this is very simple. We just take the tentative distance of the current node and add it to the edge cost. So for B, we have a new distance of 3, because that's 0 plus 3. and we now replace our old distance of infinity with our new distance because the new distance is smaller than the old distance. Now we do the same thing with node C and we update the distance to 6 because that's just 0 plus 6. So now that we've done this with our current node A, we say that A has been visited and its tentative distance is locked in as its true minimum distance, which is 0, and then we move on to other nodes. So the procedure for choosing our next current node is to go to whichever node among the unvisited nodes has the lowest current distance. So this would be node B. So now we repeat the exact same procedure. The distance of C is updated to 4, because that's less than 6, and the distance of D is updated to 4 as well, because it's less than infinity. So now we say that B has been visited, and we lock in its shortest distance value of 3. So now we can sort of begin to see why Dijkstra's algorithm works. In order to get from A to B, we can either take the direct path, or we could take some route that goes through C. However, we know that any route that goes through C will incur a higher cost than the direct route, since the cost of just going from A to C will incur a higher cost anyway. So we can be absolutely certain that the shortest distance to B is 3, and that the shortest path is the direct route. Okay, so now we have to choose our next current node, and now we have a tie between C and D, so we just pick one randomly and go for C. Now we investigate all the unvisited neighbors of C. So we update the distance of F to 6, and we update the distance of E to 9. So C is visited, and we go to D. Now we update the distance of G to 9, and we see that our new distance to E is 10. However, that's greater than our current distance of 9, so we don't update it, we just ignore it. And now we can go to F. So 6 plus 3 is 9, which is the same as our current distance, so again we can ignore it. And now we can also update the distance of H to 8. So now we've reached an interesting point because we've basically determined that the shortest path from A to H must go through F. Why? Well, because the only possible alternative is G, but it takes even longer just to get to G than to get to H. So it makes no sense to go through G. And algorithmically, we know we've gotten to this point when the target node H has either been visited itself or is the unvisited node with the lowest current distance among all unvisited nodes. This is because in the latter case, it makes no sense to visit any more of the unvisited nodes because we know that we'll never get a distance value for H that is any lower than the one that we've already got. So now we can begin our backward pass, and we can think of this like tracing the reverse path. So we go from H to F, since 8 minus 2 is 6, then F to C, since 6 minus 2 is 4, then C to B, since 4 minus 1 is 3, and finally B to A, since 3 minus 3 equals 0. And then just by flipping this path, we've now found the shortest route from A to H. Nice. So now that I've demonstrated the algorithm, here's a more formal way of writing it. Feel free to pause and write it down or whatever. And now that we're armed with Dijkstra's algorithm, let's revisit the tube problem we saw at the beginning of the video, this time using the actual times between stations. So our first node is Piccadilly Circus, that's our current node. Now the current distance to Leicester Square is going to be 84 seconds, and to Oxford Circus it's 88 seconds. So our next current node is Leicester Square. The new distance to Tottenham Court Road now is 125 seconds, and to Covent Garden it's also 125 seconds. So now our new current node is Oxford Circus, and our new distance to Tottenham Court Road is 144 seconds, which is longer, so we just ignore that. So now we've visited Oxford Circus, and we realize that among all the unvisited stations, Tottenham Court Road has the lowest distance, along with Covent Garden. So, using Dijkstra's algorithm, we've basically established that the quickest route is to take the Piccadilly line to Leicester Square, then the Northern line to Tottenham Court Road, which is handy to remember if you ever find yourself in London.